Okay, so we have a pipe that has inner radius and outer radius of 17.5 millimeters and 21 millimeters, and it's subjected to some loads using like a handle around it. And what we want to find is the principal stresses at B and A. And B here, and we're going to have some dimensions to where those loads are located. I have two loads, vertical one 1500 and horizontal one of 1200 newtons. And so the distance between, we're going to need some axes here, so y, x, and z, and the distances between the center of the pipe and that 1500 load is 45 millimeters, and the same between the 1500 and the 1200 load, 45 millimeters. And then the distance from where the handle is located to where A and B are, like tiny elements, is going to be 75 millimeters. Right, and of course ZA would be facing towards the Z direction, like this, and B would be facing towards the X direction. And I want to know where the principal stresses are there. So what we're going to do is find what kind of stresses are found in both A and B. And then with the shearing and the normal stresses, we're going to use those to create a Mohr circle and calculate the principal stresses so that we can compare those to like the properties of the material. We're not going to do that up to that point, but we'll do a Mohr circle and come up with the principal stresses. Right? So besides these outer loads, and as opposed to what I've been saying in class, where we want a big expression in terms of all the variables that I have. In this case, I'm not designing anything. I'm not saying I need to find the thickness of the pipe or the outer diameter of the pipe or anything like that, or select the material. So it's not a design problem. In this case, we have everything. We have all the parameters, dimensional, and the loads. And what I want to find is the maximum stresses. So in this case, I can start calculating stuff. So one thing that we can do here, since we already know where we want to calculate those stresses, is do a cut at 75 millimeters below the handle. So if I do that, I would see something like this. This is my pipe, and I would find A here and B here. Okay, we're going to call this A, and this we're going to call B, right? This would be the cut, and this would be the ground where the base of this pipe is. Okay, whatever. So if I remove everything else from this cut up, I would have to replace all of these loads somehow, right? So the 1500 load would just be located on top of this thing, not in the center in the hole, but on that face everywhere, and it would be distributed. And of course that would cause divided by like the area, would cause a stress that would affect both A and B, a normal compressive stress. Okay, so I still have my 1500 load. I would still have a shear going in the negative X direction of 1200 newtons. So I'm going to call those V so that I identify them as a shear, and this P, so I identify them as a compressive stress for my equations of P over A and VQ over IT. Right? Also, because there's a 1500 Newton load at 45 millimeters away from the center, there's going to be a moment in the Z direction that I'm going to call M sub Z. Okay, so I can just do that over this axis, which is the Z axis. I'm going to have a moment that would be positive or negative. Would be negative because it if I'm facing it from the positive Z direction, this would be rotating clockwise. Okay, so do this a little bit better. So these are parallel. All right. So MZ, and I can actually calculate what MZ is. Again, I wouldn't be doing this if it was a design problem, but for now I'm just locating, trying to figure out what the stresses are in A and B. So I can start calculating these. MZ would be the distance of 45 millimeters times 1500. So 45 millimeters times 1500 newtons. Okay, and that would give me a value of. And okay, so what the other thing that I said is that the that moment would be negative. So negative values for that. That would be minus 67.5 Newton meters. Okay, so 0.045 meters. So that this is Newton meters. All right, the 1200 newtons load would be causing a rotation, a twist on that pipe. So that 1200 newtons times 90, 45 plus 45, would create a torque. A torque because it would be around Y. So I'm going to call this T, and T would be equal to 90 millimeters times the 1200 Newton load. Okay, so that value would be 108 Newton meter. And that would be positive because if I'm looking at it from the positive Y direction, this would be counterclockwise, so that's positive. Okay. And finally, there's a moment in the X direction due to the 75 times 1200 load. So if I'm looking at it from, if I go up and to the right, this is generating a negative moment about the x-axis, and I would just call that m sub x. So distance 75 millimeters times a force of 1200 newtons, and again negative because it would be clockwise, and this would be minus 90 Newton meters. Okay, so I have all of the loads that will affect A and B, and not all of them will affect A, and not all of them will affect B, but I have everything I need. The 1200, the 1500, the loads by themselves, I already identify them as either shear or compressive or tensile, and then the moments that will cause either a bending or torsion, shearing stresses. And again, once more, if I was doing a design problem where I'm solving for the diameter or the material or whatever, or a combination of both of them, I want expressions so that I can just change a variable and get my answer. In this case, I'm not doing that, so that's why I'm calculating these numbers as values from the beginning. So again, because it's not a design problem, I will be needing the second moment of area for my bending. So that would be that of a ring, of a hollow circle. So that's just pi over, in terms of the radius, it would be over 4. The outer radius to the fourth minus inner radius to the fourth, and this would give me a value of 79.083 times 10 to the 3 millimeters to the fourth. I would need the polar the second moment of area, which is just double of that. So same values, but instead of a 4, it's a 2 here. So basically twice of this number, 158, 166 times 10 to the 3 millimeters to the fourth. For the compressive or the tensile stress, P over A, I'm going to need the area. So the area is just pi r squared minus pi r squared, outer minus inner radius, so squared, inner squared, and this gives me a value of 423.33 millimeters squared. And that's about it, because the other, well, maybe the Q. We can do the Q. I'm going to need that, and I would be doing the Q for half a ring, where the shearing stress from shear would be maximum. So I'll show this in a little bit. We'll come back to that. But what I want to see now is what kind of stresses A is subjected to and B is subjected to. So think about the loads that I have in this cut. At this cut, I will have two moments. So for example, MZ would make this pipe bend towards the X direction, right? MZ would make this pipe, this top surface, rotate towards the positive X direction, bend in that direction. But A would be on the neutral axis. So MZ is not going to cause any bending moments. However, MX, this MX that I drew here, I can draw it here, MX, would make this pipe bend towards the negative Z direction. So this top surface would try to move towards the negative Z direction, and then A would be under tension because it would be stretching. Okay, B would be on the neutral axis of that bending, but A would be under tension. So that's the kind of thing that I want to realize for both A and B. So let's do that. The way I do that is just checking for all of the 5 external loads. So the 2 forces and the 3 moments. Obviously the torque, I'm just calling it a moment, but it would be a torque, 2 moments, and 2 loads. So the 1500 P. My options for A, I'm going to have, so I realize that there is not going to be a sigma X for A or B, because that would only happen if this was not a pipe but just like a tank, and there's an internal pressure that is causing stresses in the X direction. The only thing that can happen is sigma Y's due to bending or just compression or tension, right? So that's the first thing I'm going to identify here. For my stress element A, I will only find sigma Y's and shearing stresses. There will not be any sigma X's. Again, because for this to be pulled or compressed, I would have to have a positive or a negative pressure inside this pipe, which I cannot have. So it's only going to be sigma Y and sigma and tau XY. Okay. Now sigma Y can either come from shearing stresses, normal stresses to compression or tension or bending, which is what I just said. So it's either a PA, if that exists, P over A, or minus MY over I, right? So is this under compression or tension? Yes. Due to this 1500 load, A is going to be under compression. Okay, 1500 Newton going down, there's a reaction from the floor, so this is going to be compressed. So this does exist, and it would be equal to 1500 newtons over the area, 423.33 millimeters cubed. And of course I need that as megapascals, so I would either switch this to meters squared and then 10 to the minus 6 and then do the math. And is it a positive or a negative? So this force is going down, or basically the compressive stresses. Compressive stresses are a negative because they're under compression. So there's going to be a negative value, right? Minus whatever. And the bending would be due to M. Again, MZ would make this bend towards this direction, so A would be on the neutral axis. So MZ is not causing anything because it would be on the neutral axis. But MX is going to make this pipe bend towards that direction, making this be on the side of the tension due to bending. So MX is what I want to write here. My moment is MX. The Y would be the distance from the neutral axis, which would be here. All of this here. So basically from this to where A is located, right? From my neutral axis due to that bending, which is this, to where this is located, that would be just a radius and an outer radius. So this would be an outer radius over the I that I calculated previously. Okay. So notice that MX is already a negative value. So let's replace these values. So mx is going to be minus 90 Newton meter. The outer radius is 21 millimeters over my I, which is 79.083 times 10 to the 3 millimeters cubed. Okay, there was a minus from the equation of bending, minus, and a minus from my moment. Okay, the radius is positive, the second moment of area is positive, so negative times negative, this is going to be a positive one. Does that make sense? Yes, because this is under tension due to bending, from what I just said. So from this moment, this is under tension, so it's going up, and I want that to be a positive value. But from the 1500 load, just under compression, this would be under compression, meaning this has to be negative. So this does make sense, because this should be negative and this should be positive. And so putting these two together, I get a value of 20.4 megapascals. Right? And now I'm going to do the same for the shearing stresses. So tau xy has two possibilities. My shearing from torsion, Tc over J, and my shearing from the shearing or from resulting from that bending, which is Vq over It, transverse shear. So, is there a torsion that is causing a shear stress on A? Yes. The torsion will make the ring right above A or B to rotate counterclockwise. So I'm going to have a vector in this direction. Okay, and so I expect that tau from Tc over J to be positive, right? Because it's going towards the top right corner of my stress element. So T had a positive value here, 108 Newton meter. C is the distance from the center to where I'm calculating the stress, and the stress is being calculated on the surface, both for A and B. I'm worried about A for now. So this would be the radius, outer radius. So outer radius equals to a positive value, 21 millimeters. And J I had already calculated, and like I said before, these are always positive. So 158, 166 times 10 to the 3 millimeters to the fourth. And of course you have to be careful with the meters and the millimeters, you have to change these variables. But what I get from that, I would either add it or subtract it with the other type of shear. Is there going to be a transverse shear for this stress element A? I go back, I see either the whole structure or just my cut, and I see that the only shear is in the negative Z direction, caused by this 1200 Newton load. However, because this dotted line from like that side to where B is where the maximum shearing stress would occur, and then it would be 0 and 0 here. This means that A is not the distribution of those loads, just to be clear, it would be maximum here due to a force 1200 newtons, would look something like this. Maximum at the center where Q is max, and then as I move farther away from the center, these vectors become smaller and smaller, okay, till they reach a 0 and a 0, and this is exactly where my element A is. Okay, so smaller and smaller until they don't exist at A. So basically what I'm saying here is that for A, the tau xy is only due to torsion. This would be 0. Why? Because if I stand here, I would have a shaded area to the top of this, which would be 0, or a shaded area towards the other side, which would be the whole circle, times the distance from the centroid to the centroid, from the neutral axis to the centroid of that shaded area, which would be 0. Okay, so let's say V does exist, but Q is 0, right? So that's why this is 0. And then this value is going to be equal to 14.34 megapascals. And because of what I said before, this is going to be a positive value. Okay, so why positive? Because there's a torsion, it's counterclockwise, so this would be rotating in this direction. So when I get here, it's going in this direction, which is a positive shear, right? So I already have my overall normal stress and my overall shearing stress. So I basically have these two values. So what I'm gonna do next is use the Mohr circle to find the principal values. So basically, what I have once again is just a sigma that is equal to sigma y and a tau xy, and my values are from before 20.4 megapascals and tau xy 14.34 megapascals. Sigma x, like I said before, because it's not a tank and it's not under pressure, because there's no other ways to find normal stresses in the x direction, this is just 0. Okay, so it's going to be a pretty simple Mohr circle. We don't need the Mohr circle, so basically just by having these we could calculate where the center is, then add a radius, and with those I can find the principal stresses both for the maximum shearing stress and the maximum normal stress. But let's do the Mohr circle just to practice that a little bit. So the center is at my sigma average, which is sigma x plus sigma y over 2, which is 20.4. 0 plus 20.4 over 2, so 10.2 megapascals. And my radius, which is my tau max, would be sigma x minus sigma y over 2 squared plus tau xy squared and square root of that. So this would be 0 minus 20.4 over 2 squared plus 14.34 squared and square root of that. So this is negative, but it's squared, so it doesn't matter. And I end up with a radius of 14.69 megapascals, right? So what I just said is we don't really need the Mohr circle. With these two values, I would know that my tau max is 1469, and I would compare that to the shearing strength, the property of the material, shearing strength, and see if it's higher or lower than this, to see if the pipe is failing. And with my average, and if I add a radius, I would end up, since my average is positive, if I add a radius, I would end up with the highest normal stress. So what I'm saying is, since it's positive at 10.2, okay, I will not subtract the radius, because I would end up somewhere here, which is not going to be the maximum. Even a maximum can be a negative value, but in this case it isn't, because my center is on the right. So if I add a radius, which is almost 15, so this maximum principal stress, sigma 1, is what I'm interested in, and it would be equal to 10.2, which is the center, plus a radius, 14.69. So this would be equal to 24.89 megapascals. Okay, sigma 1, which is my sigma max, right? And that is what I would compare to the, I don't know, the tensile yield strength or something like that. All right, but let's finish this just to practice. So this is my sigma 1, this is my sigma 2, which would be basically my center minus a radius, 14.69. So let's say it's somewhere at minus 4 megapascals, something like that. Then the radius is 14.69, so I would go up 14.69 up and down from the center to know more or less how this Mohr circle would look like. Okay, doesn't need to be perfect, but I do need to find the values that I'm interested in. So where's my original state, stress state? So I have a y equals to 20.4. So at 20.4, basically double of this. If this is 10, this is 20.4. And 14.34 in the y, because this is x, sigmas, and y's going down tau's. So a 14.34 would be going down 14.34. I would find my original state of stress for sigma y, so that is what I call capital Y. Okay, and if I draw a diameter, obviously passing through the center, I would find my original state of stress is for x, which makes sense. Capital X is where my sigma x would occur. So sigma x is 0. Is this 0 on the x-axis, which is the sigmas? Yes. And at tau of minus 14.34 megapascals. So that does make sense. Now again, I was just interested in this problem to find my sigma max and my tau max. So it can be either here, which is a radius, which is what I found here. So my tau max is equal to 14.69 megapascals. Just those two things I was interested in, because I can compare this to the shearing strength and the tensile strength, right? So I was not interested in the angle, but I might be, to know if a crack is going to occur at some angle specifically, or I don't know, if I can reinforce the pipe somehow. So just to practice that, I would go from my y to principal stress, and that would be called 2 theta p, right? So from the Mohr circle, I don't need to remember what the equation is. I can either use the equation, or I can just use opposite over adjacent and do a tangent of 2 theta p, right? So tangent of 2 theta p in this case would be this, which is the original 14.34 megapascals, this component y, sorry, and then adjacent, which would be 20.4 minus 10.2, or basically 10.2 megapascals. And then I would find my sigma tau p. And just to finish this, the angle that I'm interested in is theta p, not 2 theta p. 2 theta p is what we get inside the Mohr circle. So if I'm interested in theta p, I would just divide that by 2, and that means that whatever angle I get here, which I know it's positive because it's to get from my original state to the principal stresses, I move counterclockwise, is what I would move this element here. So basically, I have this situation. If I have my original stress element here, and I already know what theta p is, and I know that that is going to be counterclockwise, theta p, I would find at that angle, theta p, I would find a sigma y that is now the maximum and positive, sigma y equal to this maximum value, 24.89, right? An x, I would also find an x. So if I draw the diameter from this point to the other point where my y prime and x, capital X prime are, I would find what I said was close to minus 4. So minus 4 in the x direction, sigma x equal to minus 4. And no shearing, because when I'm on the principal stress line, I wouldn't have any shearing. Okay? So compressive in x, tension in y. But I could also move 2 theta s to find my maximum shearing stresses. Okay, so that would basically mean that from my original state of stress, I could move clockwise to find my maximum shearing stress. So from this, I move clockwise as sigma s, and I would find where my maximum stresses are. So if I'm here, this would be positive. So this would still be positive values for shearing, meaning in this direction, tau xy, and they would be equal to my maximum shearing stress, which is 14.69 megapascals. Would I have x and y, sigma x and sigma y in that situation? Yes, they would both be equal to 10.12, 10.2 is the 2, and positive. So basically, I do have that where my maximum shearing stress occurs, but I also have positive sigma y's and sigma x's. So outside of x and outside of y. Okay, equal to 10.2 equal to 10.2. Okay, and that would be a complete procedure to solving for the Moore circle. And now I'm not going to do a whole thing for the other element b, but I just want to recognize what kind of stresses this stress element b is subjected to. So basically what I did here for a, but now for b. Okay, so if I look at this again, I know that b will have stresses in the y direction, no stresses in the x direction. Do exist for y, doesn't exist for x. And there's going to be shearing, so tau xy. So this is pretty simple. Basically the same for the y that I did before for element A. Now we're going to do it for b. So there is a compression. It's the same due to the 1500 divided by the area. So P over A, and that P is negative because it's going down, or basically B is being compressed by that, times the area that I have. So that exists, and it's going to be a negative value. And then sigma from the bending minus my over I. So what m do I need? If I'm looking at B, mx would be trying to bend this pipe in that direction, basically meaning that B would be on the neutral axis. So I don't need mx. I would need mz, because mz would try to make this pipe move towards the positive x direction, making B be under compression. So I expect this value also to be negative. So it's going to be a minus an mz, which is what I just said, times y, so the distance from the neutral axis to where B is located is also an outer radius, and I. This is positive, and mz, from what I said before, is going to be, mz is also going to be a negative value, right? So, like I said, because of that moment, mz, this would be under compression, and I expect this to be a negative value, right? Right, so I add these two and I have sigma y. And then just to finish, the tau xy would either be due to torsion, or both, torsion or shearing, or both. So torsion, it's the exact same situation that as in A. The torque is rotating this upper disk in this direction. So I see a vector here, and I also see it here. So that would be a positive value. So this is Tc over J. The positive value of T, the value for T is positive because it's counterclockwise. The C is the outer radius, and J is a positive value. So those are all positive values, which makes sense because this needs to go towards the right. And then for the shearing, due to shear, I have this force of 1200 newtons, which is going in the negative z direction, and I know that it is going to be maximum here on this dotted line, where is exactly where B is located. And then for that, I would have a V Q over IT. So Q I didn't calculate it, but we can calculate it for a ring. So basically what I said is I would have an equation to know where the shaded area and then times the distance from the neutral axis to the centroid of that shaded area is. And I have V, the 1200 newtons, and then I and T. And T being the width of the section that I'm looking at. In this case for B, T would be 2 times the outer radius. Okay, I have 2 times the outer radius, Q I would be able to calculate, and V would just be this shearing force 12 newtons. And I know that this value should be positive because these vectors from the stresses would be going in that direction, okay, which is positive for my small element B, right? I have a value for this, I have a value for this, And I repeat the process that I did for the Mohr circle, now with a known sigma y and tau xy. Okay, I compare the principal stress that I get there to the principal stress that I got from A. I compare the maximum shearing stress that I got from B to this one, and I see which one is greater, and then I compare the largest value to the shearing properties to see if either A or B is where the pipe would fail.